Hello everyone. We have seen basics of regression, simple linear regression as well as multiple linear regression, and we have also seen how various sums of squares could be used for developing the theory of regression. So today we will actually see the rigorous proofs for the distribution theory results that we used there. For example, we used F statistic, which was actually used for testing the significance of the regression model, etc. So today we will see some theoretical results related to sums of squares in regression. So they could be either about regression sum of squares or residual sum of squares and so on. Okay, we will first study regression sum of squares, which we know is defined as sum over I going from 1 to n yi hat minus y bar whole square. This is called as regression sum of squares because it tells me what is the effect of regression. Because without regression, I would predict everything by y bar. Now with regression, I'm predicting the outcome for xi by yi. Okay. We already know that y hat has, as a vector, y hat has a matrix representation which is x into beta, that is x into x prime x whole inverse x prime y. Correct. We have seen this. My x is n cross p matrix, my y is n cross 1 vector, this is n cross p cross p cross n, so overall n cross n and then n cross n, which gives me n cross 1 vector y hat. So this is a vector notation for y hat. I could write similar vector notation for y bar. So y bar, what we know is 1 upon n, sum over I going from 1 to n yi. So this I could write in the vector form. So I could write this as 1 upon n u prime y, where u is basically a vector of ones. So I have ones. So it's a vector of order n cross 1. So I will have 1 times y1 plus 1 times y2 plus 1 times y3 and so on. Okay. So now I have a vector notation for both of them. Okay. We are going to use these. Now before that, so for y bar I have a vector notation, but there is some scalar n which is coming in picture. Can I somehow make that n also as a vector? Okay. So what I'll have is n, I could actually write as u prime u because it will be 1 plus 1 plus 1 n times. Okay. In that case, my y bar becomes u prime u inverse because it is 1 by n and u prime y. Okay so far? So y bar is now u prime u inverse u prime y. Now let us try to see if we can express regression sum of squares in matrix notation. So I have my SSR as sum over I going from 1 to n yi hat minus y bar whole square. Okay, so this y bar is still a scalar. So when I want to express this in the vector form, I will have to convert it to a vector. So I could write u into y bar. So this will actually be basically y bar, y bar, y bar. So scalar y bar repeated n times. Correct? So we are going to use that now. So for y hat, I already have a vector. So this sum of squares I could write as y hat vector minus my y bar vector. Y bar vector means I would write u times y bar scalar prime because I want finally sum of squares, which will actually be dot product, So y hat vector minus u y bar. Okay. So now I have a vector notation. Now I will substitute value of y bar and y hat. So y hat we know from above is x prime x whole inverse x prime y. That is my matrix or vector representation for y hat. Then I have this u, and y bar we just now wrote is u prime u whole inverse u prime y. Okay, whole thing transpose, and I'll have same thing. So I again have x prime x inverse x prime y minus u prime u inverse u prime y. Correct? Okay. Now this is transpose, so I could actually write this as y prime. Y is common, correct? And here also y is common, so I could take that y outside and I could then apply transpose. So this will become y prime into this whole matrix prime. So this whole matrix I will write as x prime x whole inverse x prime, because y now I have taken common, minus u prime u whole inverse u prime, whole thing into prime, and inside I have same stuff. So I have x prime x inverse, then I have x prime y minus, sorry, y is not there because y we are taking out. So simply minus u prime u inverse u, and then outside y. Okay. So I have y prime into transpose of some matrix into that same matrix into y. Okay. Now what is our X matrix? If you recall, my X matrix is basically first column is U, vector of ones, and remaining entries is a matrix formed by actual regressor values. So I could partition X as U into XR, where XR will be of order n cross k if I have k regressors. Okay. So we have some identities for partition matrices which we are going to use here. Okay. What are those identities? Let me first code those results and then we will apply those to this particular situation. So first let me write the result that we are going to use. Okay. So the result to be used. So in general, suppose I have a matrix M which could be partitioned as say M1 and M2, then, and I'm interested in something like this, right? X prime x whole inverse x prime. So we will use that. So actually what I have is M, then M prime M whole inverse. Now I write suppose M prime M. So what is this? If M prime M is invertible, then M prime M inverse M prime M is identity. So this is basically equal to M matrix. Okay, because M prime M inverse and M prime M will make it identity. So if I now write in the partition form, then I have M prime M inverse, and okay, this first M prime I will keep as it is, and this M I will now write as M1 M2, and on the right side also I have M1 M2. Okay, so what do I have? Because of the theory of partitioned matrices, now what I'm getting is the first part, that is m m prime m inverse m prime into m1 is my first entry. First entry means first part on LHS, and m prime m inverse m prime m2, that is my second part on LHS, and right hand side I have m1 m2. So basically what I get is m into m prime m whole inverse m prime m I is equal to mi for 1 as well as 2, correct? And if the two matrices are equal, then I could take transposes and they would still stay equal. So if I take transpose of this identity, what would I get? I would get mi prime, then m prime prime will become m, because I'm taking transpose, I'm writing in the reverse way. So mi prime, then m prime m is symmetric, so m prime m inverse stays as it is, and then m prime is equal to mi prime again for both eyes. Okay, so far? So we are going to use this result for x. Okay, so let me go back to whatever x we had. So the x we had is this. So x is now u xr. So I am going to treat u as x1 and xr as x2, and I'll use the results. Okay, so let me write what this result implies. So this result now implies the result that we proved just now. That implies that I will have x prime x whole inverse x prime u is equal to u from the first part. Okay, right now I'm not going to need the second part identity. I will just use the first part identity. And from the transpose, I have x, sorry, I'll start with u prime. So u prime, I'm just taking transpose of this equation like we did there. So u prime x, and then x prime x inverse x prime is actually equal to u prime. Okay. Now, why we are doing this? We are doing this because we want to finally prove that the matrix that we have in between y prime and y has some special property, that basically it is idempotent. So let me consider that matrix which is present between y prime and y. So let us just see what the matrix is. See, the matrix is this: x prime x whole x prime x whole inverse x prime minus u prime u whole inverse u prime. So we have to check whether that matrix is idempotent. Okay. So I will consider square of that matrix here. So I have x prime x whole inverse x prime minus u prime u whole inverse u prime. I need to consider square of that, so I will multiply by the same matrix. x prime x whole inverse x prime minus u prime u whole inverse u prime. Okay, so what do I get? Let me see. So what I will have first is, so we will have this term multiplied by this term and so on. So first term becomes x prime x whole inverse x prime into first term from the second bracket, that is x x prime x whole inverse x prime. Okay. Then first term from first bracket and second term from second bracket. So this becomes minus x prime x whole inverse x prime into u prime u whole inverse u prime. Okay. Then I have second term from first bracket and first term from first term from second bracket. So this will be u prime u whole inverse u into u prime into x prime x whole inverse x prime plus final term is u prime u whole inverse u prime into u prime u whole inverse u prime. Okay. Okay, now see what I have. What I have is now x prime x whole inverse x prime x. So this becomes identity. Then here also similarly this becomes identity. So my first term is x prime x inverse x prime. Last term is u prime u whole inverse u prime. I need to worry about two in between terms. Now for the in between terms we are going to use the results that we quoted. So what we quoted here is this. Okay. So x prime x whole inverse x prime u. So x prime x whole inverse x prime u is basically u, and similarly from this third term the last part, that is u prime x prime x whole inverse x1 prime x prime is basically u prime. Okay. So first part of second term and second part of third term. Okay. So this part, let me, okay. So this part becomes u because of that result, and this part becomes u prime. Okay. So let me now write those. So I have u prime u whole inverse u prime, and the third term becomes u prime u whole inverse u prime. Correct. So basically I have same term now occurring thrice, but with two minuses and one plus sign. So what I get is x prime x whole inverse x prime minus u prime u whole inverse u prime, because this term gets cancelled with this term. Okay. And this is exactly the original matrix that we started with. Hence, we have now proved that this matrix is idempotent. Okay. So, if I have an idempotent matrix, then we have some theory from distribution theory which can be used here. So, what is that theory? So, let me try to write. One of the major assumptions in a regression model is that errors are uncorrelated. Okay. And they're having constant variance. So we have variance of epsilon vector as sigma square constant into identity matrix, correct? So if I consider SSR upon sigma square, that would become 1 upon sigma square, and SSR we just now showed that the matrix is idempotent, and hence I will have that matrix only occurring once. Okay, it is anyway symmetric and idempotent, so I will have 1 by sigma square y prime into the matrix, that is x prime x whole inverse x prime minus u prime u whole inverse u prime whole into y. Okay. So we are going to need a result from distribution theory. For that, let me state the basic setup. So I have, suppose, a k-variate vector which follows normal distribution with mean mu and variance covariance matrix V. Okay, so Y is a k-variate normal vector. And suppose A is a k cross k matrix of constants. Okay, A is a k cross k matrix of constants. And of course, we are assuming that this V is non-singular. Okay, now we define a quadratic form, say Q as, of course, Q will be scalar. So we define Q as y prime a y. Okay. If Q is defined as y prime a y, then the results from distribution theory tell me that if A into V or V into A is an idempotent matrix with rank P, then this quadratic form Q has chi-square distribution with degrees of freedom P and non-centrality parameter lambda, where lambda is mu prime a mu. Okay. So V is the variance covariance matrix of vector y. So if AV or VA is an idempotent matrix, then Q follows chi-square distribution with P degrees of freedom and some non-centrality parameter. We are now going to use this result to say something about distribution of our regression sum of squares. Okay. So we have just now proved that the matrix that we have in regression sum of squares, this matrix is idempotent, and we know that we assume normality of y, correct? And because of the uncorrelatedness assumption of residual of errors, what we get is that y will also have normal distribution with identity matrix sigma square into identity matrix as variance covariance matrix, correct? As a result, now my V is sigma square into I, correct? What is my A matrix here? A matrix is this matrix divided by sigma square. So A into V is basically this matrix. And we already proved that this matrix is idempotent. Let me repeat what I am saying. So in this particular case, my A matrix is 1 by sigma square into the big matrix. So V into A is basically the big matrix because variance covariance matrix is sigma square into I. So sigma square gets cancelled. And we have proved that this is idempotent. The matrix in the square brackets here is idempotent, that we have proved. So we will use this result to conclude that y prime ay will have chi-square distribution. Okay. For that, now for getting degrees of freedom, I will need rank of this A. So let us consider rank. Now since this is an idempotent matrix, rank is basically equal to trace. That is a property that you studied in linear algebra. So let me see if I can consider trace so that I can get rank. So what we know is rank of that big matrix is equal to trace of that same matrix. So let me consider trace. So trace of the matrix is x prime x whole inverse x minus u prime u whole inverse u prime. Oh, sorry, x prime x whole inverse x prime and u prime u whole inverse u prime. Now trace of a minus b can be written as trace of a minus trace of b. So I will have trace of x prime x whole inverse x prime minus trace of u prime u whole inverse u prime. Okay. We know trace has a nice property that trace of a into b is same as trace of b into a. In fact, trace can be rotated cyclically. So trace of a b c is same as trace of b c a, or same as trace of c a b, and so on. So we will use that property. So I will have trace of, so x I will bring here. So it will be x prime x whole inverse x prime x. Okay. Similarly here I will write this as trace of u prime u whole inverse u prime u. Okay. So what do I get? So x prime x whole inverse x prime, it is trace of identity matrix of order p, because x is of order p cross p. Okay. And what do I get here? Now u prime u is basically a scalar. U prime u is n inverse n. So basically it is 1. So trace of 1 means just 1. So this becomes p minus 1, which is our k, that is number of regressors. Okay. Hence, the degrees of freedom for chi-square distribution for regression sum of squares is k, that is same as number of regressors. Okay. Now we have to worry about the non-centrality parameter. Okay. So what is lambda? So if my model is correct, then we know that expectation of y vector is x into actual beta, correct? So I could write this as x, I will again partition as u vector and the matrix of regressors xr, and beta I could partition as beta naught into a vector consisting of all regressors, coefficients for all regressors. So this I could write as beta naught scalar into u vector plus xr matrix into beta r vector. Okay. Again, we are using the theory of partition matrices. The non-centrality parameter from the chi-square result is mu prime a mu. So mu was mean of y. So now this is my expression for mean of y. Correct. So let me write that, and A matrix we know is that big matrix divided by sigma square. So my lambda becomes 1 by sigma square expectation of y whole prime into the big matrix. So x prime x whole inverse x prime minus u prime u whole inverse u prime into expectation of y. Okay, y. So mu prime, mu is expected y, then the matrix, and then mu. That is my non-centrality parameter. So A is that big matrix divided by sigma square. Okay. So let me substitute expectation of y. So expectation of y we know is x beta. We know expectation of y is x beta. So let me substitute. So this is x beta prime into this big matrix into x beta. Okay, x is a matrix and beta is a scalar. Then we will use the partition matrices that we constructed just now. So 1 by sigma square. So x beta whole prime actually becomes beta prime into x prime. So let me write beta prime. Beta prime will be beta naught because it's a scalar, and then beta r vector prime. Okay. Then I have x matrix with prime. So that will become u prime and x r prime. Okay. Then we have the original big matrix as it is. Then we have x, which we would write as u xr, and beta, which we would write as beta naught and beta r vector. Okay, so far? Okay, so let me now write this matrix and try to take products. So I have 1 by sigma square, beta naught, then beta r prime, u prime, xr prime. This matrix is x, x prime x, sorry, x is a matrix. So x, x prime x inverse. Oh, why did this vanish? I didn't do anything. U prime and xr prime is there. Okay, so x prime x whole inverse x prime minus u prime u inverse u prime into this u xr stays and beta naught beta r stays. Okay. Okay, what do I have? So let me take the products. So this beta naught and beta r prime, right now I will keep as it is. So from this product, what do I get? So this is like 2 cross 1 in the partitioned setup. This is like 1 cross 1. So I should finally get 2 cross 1. So this into this will be one entry and this into this will be another entry. So I will have u prime into x, x prime x inverse x prime minus u prime u prime u whole inverse u prime as first entry. Second entry will be xr prime, okay, xr prime x, x prime x whole inverse x prime minus xr prime u prime u whole inverse u prime. Okay, this is what u prime u. Okay, and this is as it is. So I have u here, I have xr here, and we have beta naught here and beta r here. Okay. So can we do something about this? Now from the earlier result, we know that this u prime into x prime x whole inverse x prime is basically u prime. We had proved it. Okay. If you go back, you can check it. And here this u prime u and u prime u inverse will get cancelled. So I'll again have u prime. So I have u prime minus u prime. So my first term becomes simply 0. Okay. So I have 1 upon sigma square beta naught, and then I have beta r prime. This entry becomes 0. Okay. Of course, it is a vector, okay, of appropriate order. So the order is same as order of u prime, right? So it is kind of like 0 prime if I consider 0 as a column vector. What do I have here? Now I will use that same result. We knew that XR was another part of that partitioned matrix. So I will use that same result. So XR prime, this will actually be simply XR prime. Okay. So let me write that. So I will have, from the same result of partition matrices, this will become xr prime. Second term I will keep as it is. So I have xr prime u, u prime u inverse u prime. And then I have this u xr, and I have this beta naught beta r. Okay, so far? Okay. So let me now take this product. Uh, so what is the order here? So here I have kind of like 2 cross 1, and I have kind of like 1 cross 2. So it is going to become 2 cross 2. Okay. So let me see. So the first thing I will keep as it is, this beta naught and beta r prime. Now this becomes 0 prime into u. So this stays 0. 0 prime into u becomes now a scalar 0. Then 0 prime into xr becomes vector 0. 0. Then I have xr prime u minus xr prime u, u prime u inverse, u prime u. Okay, let me write, and then at the next step we will do something. So this is xr prime u minus xr prime u, u prime u inverse, u prime u. Okay, I'm not cancelling it. Yeah, u prime u. Okay, and the last term becomes, so ideally I should not write this 0 here. So where should I write it? I should write it somewhere here. So 0 prime. And the last term now becomes xr prime xr minus xr prime u, u prime u whole inverse, u prime, and then xr. Okay. And my beta naught and beta r remains. Beta r is a vector. We shouldn't forget that. So beta r, it stays here. Okay. So you can see here, this is xr prime u. Okay, and I have u prime u inverse, u prime u. So u prime u inverse and u prime u gets cancelled. So I have xr prime u again. So this term also becomes 0. Okay, so what I'm left with is just this term, xr prime xr minus xr prime u prime u whole inverse, u prime xr. Okay, so I have 1 by sigma square. Now because of, okay, so this is 0. So now because these three terms are 0, my beta naught will actually vanish because it will get multiplied by these zeros. So what I'm left with finally from this product is beta r prime, then, so just the fourth term, beta r prime xr xr minus, sorry, these are matrices, not scalars, xr prime u, u prime u whole inverse, u prime xr whole into beta r. This is the term that remains because all other three entries are 0. So I get only the last entry. Okay. So this becomes my non-centrality parameter for that chi-square distribution. Okay. If we if we want to try and make our life a bit easy, then what we can do is we can define a matrix of centered regressor. Okay, so centered regressor values. So how will I do that? From every regressor value, I will subtract its own mean. So my centered regression matrix is it is x11 minus x1 bar, x21 minus same x1 bar up to xn1 minus x1 bar. Then I will have x12 minus x2 bar, x22 minus x2 bar, and xn2 minus x2 bar, and so on. Finally, I will have x1k minus xk bar, x2k minus xk bar, xnk minus xk bar. Okay, so this matrix is of order n cross k, a matrix of centered regressors. Why does it help? So basically, you can see here this u prime u whole inverse u prime. We have already seen this does kind of the job of averaging, right? So basically, if I take xc prime xc, then I'm going to get the same matrix that we have here. Okay, so this is homework for you. It's algebra, nothing else. So homework is you have to prove that this xc prime xc, if I consider, then we can prove that this is exactly same as the matrix in the earlier derivation. Xr prime xr minus xr prime u u prime u inverse u prime xr. Okay, it's just algebra. So you start with the RHS matrix or LHS matrix, whatever is convenient for you, or you can simplify both of them and prove that both the simplifications turn out to be the same. Okay, so this is homework, and as I said, no tricks required. This is simple algebra. Okay, so now assuming you do this homework, what we have is the non-centrality parameter is 1 by sigma square beta r prime xc prime xc into beta r. Okay, this is the non-centrality parameter. Um, we can compute expected value for this regression sum of squares. Okay, so what is expected value for regression sum of squares? It will be expected value of y prime into that big matrix. So big matrix is x prime x whole inverse x prime minus u prime u whole inverse u prime into y. This was my regression sum of squares, right? We had derived this. So I have a quadratic form inside. So basically it's a scalar. So I could write it as trace of itself. Okay. So it will be trace of y prime into this big thing y, which I could write as trace of that big thing into y prime. By using properties of trace, I could take it as y prime, and of course I'm forgetting expectation. So it is expectation of trace, again expectation of trace. Since it's a scalar, I could write it as trace, and we know trace and expectation can be interchanged. So this is trace of expectation of that big matrix into y prime. Okay, now what we know is this big matrix contains only x and u. X we are assuming are not random, so they are constant, so they won't get affected by expectation. U is anyway a matrix of ones, so it is a matrix of constants. So trace can go, sorry, expectation can go inside. So I will have trace of the big matrix into expectation of y prime. What is expectation of y prime? Expectation of y prime. So let me use some theory here. So we know variance of any vector y is expected y minus mu y y minus mu y whole prime. Okay, so this we can write as expectation of y prime minus mu y prime. So expectation of y prime is variance of y plus mu y prime. Okay, so I'm going to substitute that here. So this is trace of the big matrix into expectation of y prime is variance of y plus mu y prime. Okay, variance of y we know is sigma square I. Okay, so this becomes trace of that big matrix into sigma square I plus trace of mu y prime, of course multiplied by the big matrix. The big matrix is sitting here. Okay, now we while deriving the degrees of freedom for regression sum of squares, we actually proved that trace of that big matrix is simply k, correct? Because I is anyway a constant, so I will have k sigma square. Okay, we proved this trace is k, so it will become k sigma square. Okay, let me show you where we proved that. In case you have forgotten, let me go up. Yes, see. Here we proved that the trace of this big matrix is k. Okay, so I'm using that result. So trace is k and sigma square, and this part is actually trace of big matrix into mu y prime. By the properties of trace, I could write this as trace of mu y prime big matrix mu y, and we know mu y prime big matrix mu y is again a quadratic form which we solved for here. See, expected y is nothing but mu y, so mu y prime into big matrix into mu y is basically lambda. Of course, sigma square is not there, but other than that it is lambda. Hence, I get the second term as beta prime, beta r prime, xc prime, xc beta r. Okay, from the derivation that we did just now for the non-centrality parameter. Okay, is it clear? Let me repeat. So I'm having trace of that big matrix into mu y prime, which I could write as trace of mu y prime into big matrix into mu y by properties of trace, and then it becomes trace of a scalar, so it is same as the scalar which is mu y prime big matrix mu y, which is what we derived above to be same as this. Okay, hence what do I get? What I get is that if I consider SSR upon K, that is my MSR. So expectation of MSR is same as expectation of SSR upon K. So that will actually be same as sigma square plus this term. So beta R prime x c prime x c. Okay, I have a c here which is missing, yeah, into beta R divided by K. Okay, this is the expression for mean sum of squares due to regression. Expectation of mean sum of squares due to regression. Okay, so today we will stop here. We will talk about residual sum of squares in the next lecture. Thank you.